When you look at Earth from space, the first thing you notice is not the continents, not the mountains, not even the clouds. What captures your eyes is the blue. Oceans wrap around our world like a shining coat, reflecting sunlight into the void, making Earth stand out like a jewel in the darkness. More than 70% of our planet's surface is covered by water. From orbit, it seems endless. From the ground, standing on a shore, it feels equally infinite. The waves stretch out to the horizon, carrying a sense of mystery that has fascinated humans for as long as we have existed. But here lies a question that is older than humanity itself. Where did all of this water come from? The simple answer is not so simple. The oceans, the rivers, the rain that falls on your roof, and even the water in your own body all share a cosmic history. They were not always here. In fact, in the earliest days of Earth, our planet was so hot, so chaotic, that liquid water could not survive on the surface. Yet today Earth is drenched in it, almost overflowing. How did such a dry beginning give way to a world of oceans, lakes, and ice? To approach this mystery, we have to look far back in time and even farther out into the cosmos. Think for a moment about water itself. Every drop you see is made from 2 hydrogen atoms bound to 1 oxygen atom. Hydrogen is the simplest and most abundant element in the universe. Oxygen, though not as common, is still one of the building blocks of stars, planets, and life. When these 2 elements meet, they form a molecule that is both ordinary and extraordinary. Ordinary because water seems so familiar to us. Extraordinary because it behaves in ways that almost no other substance does. It expands when it freezes. It dissolves countless minerals. It stores and releases heat gently, making climate stable enough for life. These special properties are part of why Earth is unique in our solar system. But the bigger puzzle is not what water is, but how Earth ended up with so much of it. If you compare our planet to our neighbors, the contrast is striking. Venus, almost the same size as Earth, has only traces of water vapor in its crushing atmosphere. Mars, smaller and colder, once had rivers and lakes, but most of its water has long since escaped into space or frozen into its poles. Earth alone carries vast oceans, glaciers, and an atmosphere filled with water vapor that cycles endlessly through rain and clouds. Something made Earth different. Something gave us the gift of oceans. Scientists believe the story begins over 4.5 billion years ago, during the violent birth of our planet. Imagine a swirling disk of dust and gas surrounding a young star, the Sun. From that material, at first, it was a ball of molten rock, hammered constantly by asteroids and comets. Temperatures on the surface were so high that any liquid water would have boiled instantly into vapor. For millions of years, Earth was inhospitable, fiery, and dry, and yet hidden within that chaos were the seeds of the oceans to come. There are 2 main ideas about where those seeds came from. The first suggests that water was locked inside Earth from the very beginning, trapped in minerals deep within its mantle. Over time, volcanic eruptions and geological activity released this water, slowly creating an atmosphere that could hold clouds and rain. The second idea points to outer space. According to this theory, water arrived carried by icy asteroids or comets that slammed into the young planet, delivering their cargo of frozen molecules. These impacts could have provided vast amounts of water, enough to fill the basins that became our oceans. Which idea is correct? The truth may be a blend of both. Earth's water likely has multiple origins, some from within, some from beyond. But the details remain a mystery, and scientists continue to study meteorites, ancient rocks, and even distant comets to piece together the full story. What makes this mystery so captivating is that water is not just a feature of our planet. It is the foundation of life itself. Every cell in your body, every tree, every fish, every cloud relies on it. Without water, Earth would be barren and silent, a world of rock and dust drifting through space. With water, it is alive, green, and vibrant. The question of where water came from is not just about geology or chemistry. It is about why we are here at all. So tonight, as you listen and drift closer to sleep, picture Earth not as the familiar blue marble we know, but as it once was, a fiery ball of molten rock, waiting for oceans. Imagine the violence of impacts, the hiss of steam rising into the young atmosphere, the slow cooling of the crust, and the first raindrops falling onto a world that had never seen rain. Those first drops were the beginning of a story that continues in every wave, every river, every breath of water vapor in the air. And as we explore this mystery, chapter by chapter, we'll uncover how Earth's oceans came to be, why they have endured for billions of years, and what their presence tells us about the story of life itself. Water feels so ordinary in our daily lives that it is easy to forget just how strange it is in the larger universe. You can turn on a faucet, watch a river flow, or feel rain on your skin, and it all seems simple. But in cosmic terms, water is an extraordinary substance. It is made of the most abundant element in the universe, hydrogen, and one of the most vital elements for life, oxygen. And yet, despite this, vast amounts of the universe remain dry. Why then is Earth drenched in oceans while many other worlds are not? This question leads us far beyond our planet, out into the cosmos, to trace the deeper origins of water itself. Hydrogen, as the simplest element, was created in the first moments after the Big Bang, nearly 14 billion years ago. The young universe was filled mostly with hydrogen and helium, floating as simple atoms in expanding space. Oxygen, however, did not exist yet. It had to be forged inside the hearts of stars. When stars burned through their fuel and exploded in supernovae, they released heavier elements into space. Among those elements was oxygen. Only when hydrogen and oxygen finally met, countless generations of stars later, could water molecules form. That means the water in Earth's oceans, the water in your glass, and even the water in your own body carries the signature of ancient stars. But how does water move from the explosions of dying stars to the surface of a young planet? The answer lies in the clouds of gas and dust that fill galaxies. These interstellar clouds are called nebulae. Within them, hydrogen and oxygen can come together under the right conditions to form water ice. In fact, scientists using space telescopes have detected enormous reserves of frozen water in these distant clouds. Some of them hold more water than all the oceans on Earth combined. This discovery suggests that water is not just a local feature of our solar system. It is a cosmic substance, woven into the fabric of galaxies. When our solar system was forming about 4.5 billion years ago, it grew out of one of these clouds. Gravity pulled gas and dust into a spinning disk around the young sun. Within that disk, tiny particles stuck together, growing larger and larger until they formed planetesimals, the building blocks of planets. Some of these bodies carried water locked as ice, others held it in minerals. In time, collisions between these bodies seeded the inner solar system with the ingredients of oceans. Earth's story is just one chapter of this larger cosmic tale. One of the most surprising findings of modern astronomy is just how widespread water really is. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, hold vast subsurface oceans beneath their frozen crusts. Comets streak through the solar system with long tails made of water vapor. Even the dusty surface of the moon contains tiny traces of water molecules bound to its minerals. The universe, it seems, is far from dry, and yet the puzzle remains. Why does Earth have so much liquid water on its surface when most other worlds do not? Part of the answer lies in location. Earth formed in the so-called habitable zone of the solar system, the region where temperatures allow liquid water to remain stable. Too close to the sun and water vaporizes, as happened to Venus. Too far and it freezes, as on Mars. Earth sits in the middle, in a sweet spot where oceans can exist. But even being in the right place was not enough. Water still had to arrive here, either carried by impacts or released from deep inside the Earth. This cosmic perspective reminds us that water is both ordinary and miraculous. It is ordinary because it forms naturally whenever hydrogen and oxygen meet, conditions that occur in many corners of the universe. It is miraculous because the journey from distant nebulae, through stars, through comets and asteroids, to the blue oceans of Earth is astonishingly unlikely. You could say that every glass of water holds the memory of the stars that died to create it. So when we ask, where did water on Earth come from? We are really asking a much bigger question. How did the universe deliver this substance across light years of space and billions of years of time to a tiny rocky planet orbiting an average star? To explore that story is to see water not as something ordinary, but as something that connects us to the cosmos itself. As you drift toward rest, Imagine those early clouds of gas and dust floating in space, cold and dark, yet quietly assembling the first water molecules. Picture them freezing onto grains of cosmic dust, waiting for the moment when gravity would pull them together into comets, asteroids, and planets. The oceans of Earth, the rain that falls, even the drops on your skin tonight, all began in that quiet darkness, long before the Earth was born. In the chapters ahead, we will explore how this cosmic water found its way to Earth, how it shaped our world, and why its story continues to be one of the greatest mysteries of science. We see water every day, and yet how often do we stop to think about what it really is? A glass of water looks so simple, clear fluid, and calm. But the deeper you look, the more extraordinary it becomes. To understand where Earth's water came from, we must first understand what water itself is, because its properties are unlike almost anything else in nature. At the most basic level, water is a molecule. Each molecule is made of 2 hydrogen atoms and 1 oxygen atom, bonded together in a tiny V-shaped structure. This simple geometry gives water its familiar formula, H&O. But simplicity does not mean ordinariness. The angle between the hydrogen atoms and oxygen, along with the way electrons are shared between them, gives water polarity. One side of the molecule carries a slight negative charge, while the other side carries a slight positive charge. This polarity makes water sticky. It allows molecules of water to cling to one another and to many other substances. That stickiness is what lets water climb the stem of a plant, bead up on glass, or pull itself into droplets that fall as rain. Another strange property of water is its behavior when it freezes. Most substances become denser as they cool, sinking as solids. Water does the opposite. When it freezes into ice, it expands. The crystalline structure of ice is less dense than liquid water, which is why ice floats. If water behaved like most other substances, lakes and oceans would freeze from the bottom up, locking life beneath layers of ice. Instead, ice floats on top, creating a protective blanket that insulates the liquid water below. This single property may have been crucial for life's survival on Earth. Water is also an excellent solvent. Because of its polarity, it can dissolve more substances than any other liquid we know. Salt, sugar, minerals, and even gases like oxygen and carbon dioxide dissolve easily in water. This ability turns water into a universal carrier of nutrients and chemicals. Inside your own body, water transports oxygen, carries nutrients to your cells, and removes waste. In rivers and oceans, it circulates minerals, shaping ecosystems. Without this dissolving power, life as we know it could not exist. There is another remarkable feature of water, its ability to store and release heat. Water has a high specific heat capacity, which means it takes a lot of energy to raise its temperature. Likewise, it can absorb large amounts of heat without changing temperature quickly. This makes water a natural regulator. Oceans moderate the climate by absorbing heat during the day and releasing it slowly at night. Coastal regions experience milder temperatures because of the sea's influence. Even within our own bodies, water helps maintain a stable internal temperature. It is no exaggeration to say that water is the most unusual common substance on Earth. Few other liquids behave quite like it. This strangeness may be exactly what allowed life to flourish here. It is almost as if the properties of water were tailor-made to support complexity, stability, and growth. Scientists often wonder, is life elsewhere in the universe possible without water? Some speculate that other solvents, like ammonia or methane, might play a similar role on other worlds. Yet on Earth, nothing rivals water's combination of qualities. To appreciate how strange water is, imagine what Earth would be like if it were different. If ice sank, the oceans might have frozen solid during ice ages, leaving no liquid water for life. If water did not dissolve so many substances, the chemistry of life could not unfold. If it did not absorb and release heat so gently, climates would swing wildly, making the planet unstable. In a sense, every property of water seems perfectly suited for making Earth habitable. As you drift towards sleep, consider the glass of water on your bedside table, or the sound of rain outside your window. That liquid is far more than a drink or a backdrop. It is a molecular marvel, a substance that breaks rules and defies expectations. It flows, it climbs, it freezes, it protects, it dissolves, it carries. It is both gentle and powerful, ordinary in appearance yet extraordinary in function. Understanding water itself is the foundation of the mystery we are exploring. The oceans did not simply appear. They required a substance so unique that it could both sustain life and shape the planet. In the chapters ahead, we will step back into time, to the fiery birth of Earth, and watch as this most unusual liquid first began to gather on the surface of a world that once knew only heat and stone. To imagine the origin of Earth's water, we must first picture the Earth before there was any. The young planet was not blue, not calm, not covered in clouds and seas. Instead, it was a world of fire. More than 4.5 billion years ago, Earth was newly born from the swirling material left over after the sun ignited. It was still hot from collisions, still glowing with the energy of its violent creation, and still too unstable for oceans to exist. The solar system itself began as a vast rotating disk of dust and gas called the solar nebula. Within this disk, gravity pulled particles together, sticking them into larger and larger clumps. Over time, those clumps became planetesimals, rocky and icy bodies that collided again and again. Each collision released heat, and as they merged, they grew into protoplanets. Earth was one of these, a young world forming from countless impacts. Every strike melted rock, every merger added more heat. The result was a surface so molten that it glowed. Volcanoes erupted constantly, and rivers of lava spread across the crust. The atmosphere was not breathable air but a thick, toxic haze of carbon dioxide, nitrogen, and sulfur. The ground trembled with earthquakes, and firestorms filled the skies. If you had been there, you would not have recognized it as Earth. No oceans, no rivers, no blue skies, just fire, gas, and rock. One of the most dramatic events in this early period was the impact that created the Moon. Scientists believe a Mars-sized body, often called Theia, collided with the young Earth. The collision was so powerful that it blasted molten rock into orbit. That debris gathered to form the Moon we see today. Such an event would have boiled away any liquid water that had begun to collect. Earth was left dry, hot, and unstable. Yet within this chaos, the conditions were being set for something remarkable. As Earth cooled, its crust began to harden. Deep within the mantle, elements trapped during formation included water bound inside minerals. Volcanoes released this water as steam, along with carbon dioxide and other gases. Slowly, a primitive atmosphere thickened. But the surface was still too hot for liquid water. Any rainfall would have evaporated instantly, returning to the sky as vapor. It would take millions of years of cooling before the first stable pools could form. During this fiery beginning, the planet also experienced a period known as the Late Heavy Bombardment. Around 4 billion years ago, the solar system was still unstable. Asteroids and comets rained down on Earth, striking with unimaginable force. Each impact released enough energy to vaporize rock and heat the atmosphere. Yet those same impacts may have been carrying frozen water locked in their icy cores. Every strike may have added drops to the future oceans. The combination of volcanic outgassing and extraterrestrial delivery is at the heart of the water mystery. Some scientists argue that most of Earth's water came from within, released from the mantle over eons of eruptions. Others suggest that much of it arrived from beyond, delivered by asteroids and comets. Either way, the fiery beginning of Earth was not the end of water's story, but the necessary prelude. Out of fire came the potential for oceans. Imagine standing on that early Earth. The air would be thick with steam and smoke. The ground would shake beneath your feet as lava surged. The sky might glow red and orange from constant eruptions. Lightning storms would split the clouds, and meteors would streak across the horizon. It was a hostile world, but also one in transformation. Slowly, as heat escaped into space and impacts grew less frequent, the planet cooled. For the first time, rain could fall and remain. Drops collected in basins, streams carved into rock, and the earliest oceans began to take shape. These first oceans would not have been like the ones we know today. They were acidic, filled with dissolved minerals and gases from volcanic eruptions. The atmosphere above them was toxic, heavy with carbon dioxide and methane. Yet even in such hostile conditions, these waters were precious. They provided the first stable environments where chemistry could unfold, laying the groundwork for the earliest forms of life. The fiery beginning of Earth reminds us that creation often comes through chaos. Oceans could not have appeared without the violence of impacts, the roar of volcanoes, and the searing heat of a young planet. Fire and water seem like opposites, yet in Earth's story they were partners. Fire prepared the stage and water filled it. As you drift into rest, picture that ancient world. Picture the glow of lava fields stretching to the horizon, the constant roar of eruptions, the storm clouds thick with steam. And then, imagine the first moment when raindrops struck the cooling rock and did not vanish. Imagine water pooling for the very first time. From that moment, Earth was no longer only fire. It was fire and water together, and the story of oceans had begun. In the next chapter, we will look more closely at the water rising from deep within the earth. Volcanic breath that may have filled the sky with steam and set the cycle of rain and rivers into motion. When we think of volcanoes, we often picture rivers of lava, fiery eruptions, and clouds of ash darkening the skies. Yet volcanoes are not just makers of destruction, they are also givers. In fact, some scientists believe that much of Earth's water may have come from the breath of volcanoes, released slowly, steadily, and relentlessly from deep within the planet. To understand this idea, we have to look inside Earth itself. Beneath the crust lies the mantle, a vast layer of hot rock that stretches down for thousands of kilometers. Trapped within those rocks are small but measurable amounts of water, locked away in minerals as hydrogen and oxygen atoms. When these rocks melt, the water is released as vapor. That vapor rises with magma, escaping through cracks and vents during volcanic eruptions. In this way, Earth's interior has been exhaling water for billions of years. In the planet's earliest days, volcanic activity was far more intense than it is now. Eruptions were constant, violent, and widespread. Gases poured into the atmosphere, including carbon dioxide, nitrogen, sulfur, and most importantly, steam. Over millions of years, this process, known as outgassing, may have contributed enormous amounts of water vapor. As the Earth cooled, this vapor condensed into clouds and eventually fell back as rain. Imagine storms that lasted not for hours or days, but for centuries. The raindrops collected in basins carved into the young crust, and slowly, the first oceans were born. This idea paints volcanoes as unlikely heroes. Instead of delivering destruction, they may have been filling the skies with the raw ingredients for seas. Today we can see hints of this process continuing. Modern volcanic eruptions still release water vapor. In fact, water vapor is the most common gas expelled during eruptions, even more than carbon dioxide. Each eruption is like a tiny echo of the colossal outgassing that may have built our oceans long ago. Evidence for this theory comes not just from observing volcanoes today, but also from studying ancient rocks. Scientists have examined samples of basalt, the volcanic rock that forms much of Earth's crust, and discovered signatures of water locked within them. These signatures suggest that Earth's mantle has always carried water, and that it has been escaping steadily for billions of years. Some researchers estimate that if you added up all the water still bound inside the mantle, it might rival or even exceed the amount found in the oceans. In other words, Earth's water is not only on the surface, it is hidden within, cycling slowly between rock and sea. But the volcanic story does not stand alone. Critics of the outgassing theory argue that volcanic release alone may not account for all the water we see today. The amount expelled may have been vast, but was it enough to create oceans covering 70% of the surface? This question keeps scientists searching, comparing volcanic sources with evidence of delivery from asteroids and comets. The answer may lie in a balance of volcanoes providing a steady background flow of water, while cosmic impacts added extra surges. Even if volcanoes were not the sole source, their role was essential. Outgassing not only released water, but also shaped the atmosphere. The steam and carbon dioxide expelled created a greenhouse effect, trapping heat and helping the surface stay warm enough for liquid water to persist. Without that early greenhouse atmosphere, Earth might have frozen over before oceans could stabilize. Volcanoes, then, were both sculptors of the land and regulators of the climate. Picture, for a moment, what it would have felt like to stand near one of those early eruptions. The ground would rumble beneath you. The air would be thick with sulfur and steam. The sky would glow with ash, turning day into night. And yet, through all that chaos, each eruption would add to a cycle that, in time gave us calm lakes, wide rivers, and the rolling seas we know today. There is also something poetic about this process. Fire and water, often thought of as opposites, were bound together in Earth's creation. The heat of magma carried the seeds of oceans. The violence of eruptions carried the promise of calm waves. Without the breath of volcanoes, Earth might have remained a barren world, too dry for life to take hold. As you drift into rest, imagine the rain that fell after those ancient eruptions, drop by drop, storm by storm, filling hollows and carving streams. Imagine the steam cooling into clouds, the thunder echoing across lava plains, the rivers beginning their first journeys toward seas that had not yet formed. Volcanoes were not just destroyers. They were givers of water, givers of life. In the next chapter, we will leave the fires of Earth and look upward, outward, to the sky. For while volcanoes exhaled water from within, the heavens themselves may have delivered water from beyond, riding on asteroids that struck our young world like cosmic messengers carrying the oceans in their cores. If volcanoes were one source of Earth's water, another may have come from much farther away. Look up at the night sky and imagine the countless fragments of rock and ice drifting silently through space. Asteroids and meteorites, remnants of the solar system's birth, may have carried with them one of the most important gifts Earth ever received: water. Asteroids are rocky bodies that orbit the sun, leftovers from the early days when planets were still forming. Meteorites are fragments of those asteroids that eventually fall to Earth. Many of them contain minerals rich in water, not as liquid, but bound within their structure. Some even carry hydrated silicates, which hold water molecules locked inside. When such rocks collide with Earth, the heat of impact can release their hidden water, adding it to the growing supply on the surface. In addition to rocky meteorites, there are also carbonaceous chondrites, a special type of meteorite that has fascinated scientists for decades. These dark, carbon-rich stones often contain not only water but also organic molecules, the building blocks of life. By analyzing their composition, researchers have found that the hydrogen isotopes within some meteorites match the isotopes in Earth's oceans. This chemical fingerprint suggests a direct connection. At least some of the water in our seas today may have come from these spacefaring messengers. The idea is staggering. Imagine rivers and oceans forming not just from the Earth itself, but from countless collisions with space rocks traveling at tens of thousands of kilometers per hour. Each impact delivered more than destruction. It carried precious molecules. Over millions of years, this bombardment may have added up to entire oceans. The violence of impact was the very means of creating calm waters. One of the most intense periods of this cosmic delivery was the late heavy bombardment, a time around 4 billion years ago when the solar system was still settling into its orbits. Jupiter and Saturn, the giant planets, shifted slightly in their paths, disturbing belts of asteroids and flinging them inward. Earth was struck again and again, scarred by impacts so large that some basins we see on the moon today were created during this era. With each collision came not just energy and chaos, but also potential water. The skies of the young Earth must have been a constant spectacle of fireballs, the ground shaking with every arrival. Evidence for this theory lies not only in meteorites found on Earth, but also in the surfaces of other worlds. The moon, though dry today, carries scars from the same bombardment, silent witnesses to the era when Earth was struck. Mars, too, shows signs of early impacts in water. Even small asteroids we visit with spacecraft reveal traces of hydrated minerals, hinting at their role in seeding planets with water. Still, the asteroid theory is not without its questions. Some studies show that the isotopic signature of certain meteorites does not perfectly match the water in Earth's oceans. If asteroids were the main source, why is there a mismatch? Could it be that only certain types of meteorites contributed, or that asteroids provided some water while comets and volcanic outgassing provided the rest? This leads to a deeper realization. There may not be a single source of Earth's water. Instead, it may be the product of many streams, volcanic release, asteroid delivery, and cometary impacts all working together across millions of years. The ocean you see today is not the legacy of one process, but a symphony of cosmic and planetary events, each playing its part. What makes the asteroid hypothesis so compelling is the link it provides between water and the origins of life. If meteorites brought not only water, but also organic molecules, then they were delivering more than seas. They were seeding Earth with the ingredients of biology. Life may have begun not only because water was here, but because the raw materials for cells, proteins, and DNA arrived alongside it. Each falling rock was a messenger, carrying both liquid and life's blueprint. As you drift deeper into rest, picture that ancient bombardment. Imagine standing on the cooling crust of Earth, watching streaks of fire light up the sky, knowing that every burst of light might be carrying the future oceans. Picture the smoke rising as a meteorite strikes, the ground trembling, and then, after the dust clears, molecules of water released into the air. Chaos and creation, destruction and renewal. This was the rhythm of the young planet. Today, we still see echoes of this process. Meteor showers trace lines across the night sky as tiny fragments burn up in our atmosphere. Most of them are too small to deliver water now, but they are reminders of a time when such impacts shaped the destiny of our world. Each falling star you see may be a spark of memory, linking us back to the days when Earth was still collecting the water that defines it now. In the next chapter, we will look more closely at comets, the icy wanderers of the solar system. For if asteroids were rocky messengers, comets were frozen couriers, carrying vast reserves of ice from the outer reaches of the solar system into the heart of the inner planets. Their role in Earth's watery history may be just as important and just as mysterious. If asteroids were the rocky messengers of water, comets may have been its icy couriers. Unlike asteroids, which are mostly rock and metal, comets are composed largely of ice mixed with dust and organic compounds. They are often described as dirty snowballs, frozen relics from the outer regions of the solar system. When they pass near the sun, their surfaces vaporize, creating bright tails that stretch across the sky. These glowing travelers have fascinated humans for centuries, seen as omens, mysteries, or wonders. But to science, comets represent something more profound: possible carriers of water to Earth. The idea seems natural. If comets are made of ice, then each time one collides with a young planet, it could deliver water in massive quantities. In Earth's early days, when impacts were common, countless comets may have struck the surface, releasing their frozen cargo into the atmosphere. The water vapor could condense into clouds, fall as rain, and help fill the growing oceans. Some scientists once believed comets might be the main source of Earth's water, delivering enough frozen material to explain the vast seas we see today. Evidence for this hypothesis comes from the composition of comets themselves. Space missions like the European Space Agency's Rosetta probe, which studied comets 67P Churyumov-Gerasimenko, and earlier missions to Halley's Comet, revealed that comets carry not only water but also carbon-based molecules, ingredients essential for life. This makes them compelling candidates for having contributed both the oceans and the organic chemistry that life requires. If Earth was bombarded by comets early in its history, then each impact was not just the delivery of water, but perhaps a spark of biological potential. But the comet hypothesis faces challenges. The most important clue lies in something called the deuterium to hydrogen ratio, or DGH ratio. Deuterium is a heavy isotope of hydrogen, and by comparing the ratio of deuterium to hydrogen in water, scientists can create a kind of chemical fingerprint. Earth's ocean water has a specific DGH ratio. When scientists measured the water from several comets, they found that in many cases, the ratios did not match. The water in those comets was heavier, with more deuterium than Earth's oceans. This suggested that not all comets could have been the main contributors to our water. However, the picture is more complicated. Some comets, particularly those originating from the Kuiper Belt, a region beyond Neptune, have water with a DH ratio closer to that of Earth. This raises the possibility that certain comets, especially from specific regions of the solar system, did play a role in seeding Earth with water. It may not have been all comets, but a particular population that contributed. The story, then, is not simple rejection or acceptance, but a puzzle of sources and proportions. It is also possible that comets worked in concert with asteroids. Asteroids may have provided water with a D/H ratio matching Earth's oceans, while comets delivered additional amounts and brought with them a wealth of organic compounds. This partnership could explain both the volume of water and the chemistry needed for life. Rather than seeking a single source, many scientists now believe Earth's oceans are a mixture, a blending of contributions from both rocky and icy messengers. Still, the romantic appeal of comets as water bearers remains strong. Watching a comet blaze across the night sky, it is easy to imagine its icy core colliding with Earth billions of years ago, leaving behind the rain that would one day form rivers and seas. Each comet, in this vision, was a traveler from the edge of the solar system, bringing gifts of water and life to a barren world. Consider for a moment what such an impact would have been like. A comet, moving at tens of kilometers per second, slams into the Earth's surface. The explosion releases energy greater than thousands of nuclear bombs. The ice within vaporizes instantly, billowing into the atmosphere. For days, the skies would glow with heat and dust. But after the chaos settled, clouds would form and rain would fall. The violence of the strike, paradoxically, created the calm of an ocean. Modern science continues to probe the comet hypothesis. Missions like Rosetta, as well as observations from powerful telescopes, seek to refine our understanding of comet chemistry. Each new measurement adds a piece to the puzzle of Earth's water. Even if comets were not the sole source, they remain critical to the story, reminding us that our oceans may have begun as frozen crystals drifting in the dark far from the sun. As you relax into the quiet of the night, picture those distant regions of the solar system, the Kuiper Belt, the Oort cloud, where trillions of icy bodies still orbit. Imagine them as guardians of frozen seas, waiting silently for billions of years. Some may one day be nudged inward, their long journeys bringing them past the Earth again. They are reminders that our water may have started as ice carried across unimaginable distances, drawn by gravity into the heart of a young, fiery planet. In the next chapter, we will turn from the cosmic deliveries of asteroids and comets to the Earth itself, to see how once water arrived, it began to circulate in endless cycles, rising as vapor, falling as rain, and carving the landscapes we know today. The story of water is not only about its arrival, but also about its movement, its rhythm, and its eternal return. Once water had arrived on Earth, whether from volcanoes, asteroids, comets, or some combination of all three, a new story began. It was not just about water existing on the surface, but about how it moved, transformed, and sustained balance. This is the story of the water cycle, a system so elegant and powerful that it has operated for billions of years, shaping the planet and making life possible. The water cycle is, at its heart, simple. Water rises into the air, falls back to the ground, and flows toward the oceans. Yet within this simplicity lies a profound complexity. Evaporation, condensation, precipitation, and collection are the main stages, but each connects with climate, geology, and biology in intricate ways. The cycle is not just a process, it is the heartbeat of Earth's environment. Picture a drop of water resting on the surface of an early ocean. The sun warms it, giving it enough energy to escape into the air as vapor. Rising higher, it cools, clinging to other molecules, forming a cloud. When the cloud grows heavy, the drop falls as rain, perhaps onto bare rock or into a growing river. The river carries it back toward the sea, and the journey begins again. This endless recycling means that the water we drink today may have traveled the cycle countless times since the dawn of the planet. Every drop carries with it a history billions of years old. In the earliest days, the cycle must have been even more dramatic than it is today. The young sun shone slightly dimmer, while volcanic eruptions pumped vast amounts of steam into the sky. Storms would have raged for centuries, filling new basins with water, carving valleys, and smoothing rocks. Rain and runoff dissolved minerals, enriching the seas with salts and nutrients. Step by step, drop by drop, Earth was transformed from a dry, fiery sphere into a living water world. The water cycle did more than move liquid. It shaped the very face of the planet. Rivers carved canyons, floods spread fertile soils, and glaciers sculpted valleys. In time, these processes created the landscapes we know today. Without the cycle's constant motion, Earth's surface would be static, barren, and lifeless. Instead, the world became dynamic, ever-changing, alive. Another remarkable feature of the water cycle is its role in stabilizing climate. When water evaporates, it absorbs heat, cooling the surface. When it condenses into clouds, it releases that heat back into the air. This constant exchange smooths out temperature extremes, creating climates where life can thrive. Oceans, with their vast capacity to store heat, act as regulators for the entire planet. Without this balance, Earth might swing wildly between extremes of heat and cold, hostile to life. Biology too soon became part of the cycle. Plants draw water from the soil and release it through their leaves in a process called transpiration. Forests act like giant fountains, pumping vapor into the sky. Animals, including humans, drink, sweat, and breathe, all of which move water through the system. In this way, life is not just a passenger in the water cycle, it is a participant. Every living thing is both shaped by and contributes to the eternal motion of water. It is humbling to realize that the water in your glass may once have been part of a storm that raged millions of years ago. It may have frozen in a glacier, flowed in a river, or fallen on the leaves of the first forests. Water remembers no boundaries. It is recycled endlessly, connecting past and present, linking all living things through time. As you relax into quiet, imagine the cycle unfolding around you. Picture clouds gathering in the sky, droplets forming and falling as rain. See rivers winding across valleys, lakes shimmering in sunlight, waves breaking on distant shores. Picture the hidden flows underground, seeping through rocks, moving silently. Every motion, every shift, is part of a pattern that has endured since the dawn of oceans. The balance of the water cycle is fragile, yet powerful. It depends on the sun, the atmosphere, and the vast storage of oceans. It can shift with climate, tilt with geology, but it always finds its rhythm again. This rhythm is what makes Earth not just a planet with water, but a planet alive with water. In the next chapter, we will see how the cycle shaped something even greater, the oceans themselves. From shallow pools to vast basins, the formation of oceans was the turning point that made Earth truly the blue planet. The cycle gave them movement, but the basins gave them form. Together, they became the greatest feature of our world. When we look at Earth today, the oceans dominate. They cover more than 2/3 of the surface, plunging to depths deeper than Mount Everest is tall, holding 97% of all the water on the planet. But in the early days of Earth, oceans did not exist. Instead, there were scattered basins, rains that fell and boiled away, and a surface slowly reshaped by water and rock. The formation of true oceans was not instant but gradual, a story that unfolded over hundreds of millions of years. To imagine that time, picture the Earth around 4 billion years ago. The crust had cooled enough for rain to remain, and water was beginning to collect in low areas. But the surface was far from stable. Volcanoes erupted constantly, adding steam to the sky and new land to the surface. Asteroids still struck, sometimes boiling away water, sometimes adding more. It was a balance between destruction and creation. Through this turmoil, water gathered into basins, carving the first seas. The early oceans would not have looked like the blue expanses we know today. They were darker, filled with dissolved minerals from volcanic rock. Gases like carbon dioxide and methane bubbled from the crust, making the waters acidic. Instead of sandy beaches, the shorelines would have been jagged with lava flows and rocky cliffs. Yet, despite their harshness, these oceans were the first stable reservoirs of liquid water on Earth. Scientists believe that by about 3.8 billion years ago, large oceans had taken shape. The evidence comes from ancient rocks containing minerals that only form in the presence of water. These rocks act like time capsules, telling us that by then, seas had already spread across the surface. Imagine looking out over one of those early oceans. There would be no fish, no corals, no signs of life as we know it. But the waves would rise and fall, the tides would shape the land, and the rhythm of water would begin to define the planet. The formation of oceans was more than just water filling basins. It was the beginning of Earth's climate system. Oceans act as massive heat reservoirs, absorbing warmth from the sun and redistributing it around the globe. They moderate temperatures, create currents, and help shape weather patterns. From the moment they formed, Earth became a planet not only of water, but of balance. Without oceans, Earth would be a barren desert or a frozen wasteland. With them, it became dynamic and alive. One of the most remarkable aspects of oceans is their connection to the atmosphere. As rain fell and rivers flowed, minerals dissolved into the seas. These minerals, in turn, influence the chemistry of the air above. Carbon dioxide dissolved in the water, reducing its presence in the atmosphere and slowly changing the climate. Over time, this exchange between sea and sky created conditions more favorable to life. Oceans and atmosphere became partners in shaping the destiny of the planet. But the story of oceans was not only about chemistry. It was also about geology. The crust of Earth is not fixed. It floats on the mantle, broken into tectonic plates. These plates shift and move, creating mountains, valleys, and, most importantly, ocean basins. As plates pulled apart, rift valleys formed, sinking to create deeper seas. As plates collided, they pushed up land masses, reshaping shorelines. The very existence of deep oceans depends on plate tectonics constantly creating space for water to fill. Without this process, water might have covered the entire surface evenly, leaving Earth as a shallow water world. Instead, basins and continents allowed oceans to gather, shaping the blue and green planet we know. The oceans did more than simply exist. They created opportunity. Within their depths, chemical reactions occurred that may have led to the first forms of life. Hydrothermal vents on the ocean floor, spewing hot, mineral-rich water, provided energy and nutrients. In these hidden places, the building blocks of life could assemble. The oceans were not just vast reservoirs, they were laboratories where chemistry became biology. As you imagine drifting across one of those early seas, think of the silence. No birds, no fish, no sound but the waves themselves, and yet beneath the surface, invisible to the eye, chemistry was unfolding that would eventually give rise to all living things. The oceans were empty of life, but full of potential. Another fascinating thought is how familiar and yet alien those early seas would seem. If you stood on their shore, you would see waves, clouds, and rain much like today. But the air would be unbreathable, the waters too harsh to drink, and the land barren of plants. It was Earth, but an Earth before life, waiting for the spark that oceans would help ignite. Over time, the oceans grew more stable, their chemistry evolving, their basins deepening. They became the permanent feature of Earth that they are today. By the time the first simple organisms appeared, the oceans were ready, offering a home that would nurture life for billions of years. As you settle into calm, imagine those early oceans glowing under a young sun, their surfaces stirred by storms, their depths quiet and dark. They were the beginning of everything familiar: weather, climate, and life itself. The seas are not just water, they are the foundation of our world. In the next chapter, we will look at how the secrets of these ancient waters are preserved in stone. By studying ancient rocks, scientists have uncovered clues about the earliest oceans, their chemistry, and the story of how water shaped the Earth we know. To understand the story of water on Earth, we cannot rely only on imagination or theory. We must look for evidence. Thankfully, Earth itself keeps records, silent, enduring records written in stone. Ancient rocks are like pages of a book, preserving chemical signatures, mineral structures, and subtle traces of the environments in which they formed. By studying them, scientists can piece together the history of our oceans and trace the journey of water across billions of years. The oldest rocks on Earth are more than 4 billion years old. They are rare, found in only a few places such as Canada, Greenland, and Western Australia. These ancient stones carry within them isotopic clues that reveal conditions long vanished. For example, certain types of minerals, such as zircons, can survive almost unchanged for billions of years. Zircons form in molten rock, but their structure can trap tiny inclusions of other elements, including oxygen isotopes. By measuring the ratios of these isotopes, scientists can determine whether the zircons crystallized in the presence of liquid water. Some zircons, dated to about 4.4 billion years ago, suggest that liquid water existed on Earth's surface astonishingly early, perhaps only 100 million years after the planet formed. This finding reshapes our understanding. It means oceans may have appeared while Earth was still cooling, earlier than once believed. It also suggests that conditions for life were established quickly, giving biology more time to develop. These microscopic crystals, smaller than grains of sand, hold within them the first whispers of oceans. Other rocks provide evidence of how water interacted with the crust. For instance, pillow basalts, rounded shapes of volcanic rock, form when lava erupts underwater. Finding ancient pillow basalts indicates that seas already existed at the time of their eruption. Such discoveries confirm that large bodies of water covered the planet billions of years ago, even if their chemistry was different from today. Sedimentary rocks, formed by layers of material deposited in water, tell another part of the story. The presence of banded iron formations, for example, reveals how dissolved iron in the oceans reacted with oxygen, changing the chemistry of both water and atmosphere. These layers are direct evidence of interactions between water, minerals, and emerging life. By studying their thickness, composition, and age, scientists can reconstruct the shifting balance of oceans and skies. Meteorites also provide valuable comparison. Some meteorites contain hydrated minerals, showing what kinds of water, rich materials were present in the early solar system. By comparing their isotopic signatures with Earth's oceans, researchers can test whether asteroids or comets contributed to our water supply. The answers are complex, but every comparison sharpens our picture of water's origin. What makes this detective work remarkable is how precise it must be. Rocks are weathered, altered, and transformed over billions of years. Extracting tiny isotopic clues from crystals requires patience and cutting-edge technology. Scientists use mass spectrometers to measure ratios of isotopes at scales smaller than a millionth of a gram. From these delicate readings, vast conclusions emerge about oceans that existed billions of years ago. As you rest, picture the patience of this work. Imagine scientists carefully grinding ancient stones, examining thin slices under microscopes, and scanning them with beams of light. Picture zircons glowing softly as lasers measure their isotopic signatures, revealing whispers of oceans older than memory. These tiny crystals carry secrets of seas that vanished before life began, yet still tell their story to those who listen. The rocks remind us that water is both fragile and enduring. Oceans may rise and fall, climates may shift, but traces remain locked in stone. They are Earth's memory, a record no book could contain, silent yet eloquent. The study of ancient rocks also connects us with deep time. It is difficult to grasp billions of years. Our lives span only decades, civilizations only thousands of years. Yet within these rocks, we hold direct evidence of events 4 billion years in the past. Holding a zircon crystal is like holding a fragment of the planet's childhood, a tiny witness to the first oceans. These clues help answer practical questions too. By understanding how and when water appeared, scientists can refine models of planetary formation, test theories about other worlds, and even guide the search for life beyond Earth. If liquid water existed on Earth so early, might it also appear quickly on other planets? If so, the possibility of life elsewhere becomes more likely. As you sink deeper into calm, imagine those first rocks forming under alien skies, solidifying as rains fell for the first time. Picture the minerals crystallizing, quietly capturing traces of water that would last billions of years. Those rocks still lie in remote landscapes today, silent but unbroken, holding memories of the ocean's birth. In the next chapter, we will explore another force that shaped the seas and still shapes them now: plate tectonics. Moving continents, shifting crust, and churning mantle have sculpted Earth's oceans for billions of years, creating the basins that hold them and recycling water between surface and deep interior. Earth is a restless planet. Its surface may seem solid beneath our feet, but in truth the crust is broken into vast plates that drift slowly across the globe. This movement, known as plate tectonics, has shaped continents, raised mountains, and carved ocean basins. More than just sculpting landscapes, tectonics has played a critical role in the story of Earth's water: where it gathers, how it circulates, and why it has endured for billions of years. To see how, we must picture Earth's crust not as a single shell, but as a jigsaw puzzle of plates floating on the semi-fluid mantle beneath. These plates move at only a few centimeters per year, but over millions of years, they can drift across entire oceans. Where they collide, mountains rise. Where they pull apart, rifts form and seas expand. This slow but steady motion creates the very basins that oceans fill. Without plate tectonics, Earth's water would cover the surface like a shallow film. Instead, tectonics creates low places for deep seas and high places for continents. It is the reason we have coastlines, islands, and the variety of landscapes we know. One of the most important roles of plate tectonics in Earth's water story is subduction. At certain boundaries, one plate slides beneath another, plunging into the mantle. As it sinks, it carries with it sediments, minerals, and most importantly, water. Trapped within oceanic crust and sediments, water is dragged down deep into the earth. There, under immense heat and pressure, some of it is released back into the mantle, fueling volcanic eruptions. In this way, plate tectonics recycles water, carrying it between surface and interior, between sea and stone. This cycle may be crucial for maintaining Earth's balance. Without subduction, water might have simply accumulated on the surface, drowning continents. With subduction, some water is returned below, stored in minerals deep within the planet. Later, it is released again through volcanic outgassing. The balance between these processes helps regulate how much water remains at the surface, keeping oceans from overwhelming the land. Another role of tectonics is in controlling climate. As plates shift, they influence the carbon cycle. Volcanic eruptions release carbon dioxide, while the weathering of uplifted mountains consumes it. Because carbon dioxide is a greenhouse gas, this balance affects global temperatures. And temperature, in turn, determines how much water exists as ice, liquid, or vapor. Through plate tectonics, Earth has avoided extremes, keeping a climate where liquid water can persist. This is part of what scientists call the carbon silicate cycle, a natural thermostat driven by tectonic activity. The evidence of tectonics shaping oceans can be seen all around us. The Atlantic Ocean, for example, is widening as plates pull apart along the mid-Atlantic ridge. New seafloor is created there, and water rushes in to fill the gap. The Pacific Ocean, by contrast, is shrinking as plates converge, pushing water into smaller basins. These motions are slow and visible to us in daily life, but over geologic time, they are powerful forces that create and destroy seas. Tectonics also creates hydrothermal systems on the ocean floor. Along mid-ocean ridges, seawater seeps into cracks, is heated by magma, and rises back up through vents. These hydrothermal vents spew out mineral-rich water, creating unique ecosystems. They are living examples of how tectonics and water interact, not just in shaping landscapes, but in sustaining life. Some scientists even believe that life itself may have begun near such vents, in the chemical-rich waters deep beneath the waves. As you rest, imagine the slow dance of continents drifting across millions of years. Picture mountains rising and crumbling, oceans opening and closing. Imagine water sinking into the crust at subduction zones, disappearing into darkness, only to return centuries later in a volcanic plume of steam. The surface may seem still, but beneath Earth is alive with motion. Plate tectonics is one of the features that makes Earth unique. Mars and Venus show no signs of active plate tectonics today. Without this process, they lack the recycling of water and gases that stabilizes climate. On Mars, water once flowed, but without tectonics to renew the atmosphere, much of it was lost. On Venus, heat built up unchecked, turning the planet into a greenhouse furnace. Earth alone maintains this delicate balance, its moving plates acting as guardians of liquid water. So when we gaze at the oceans, we are also seeing the work of tectonics. Every coastline is the edge of a shifting plate. Every mountain range is a memory of collisions. Every deep trench is a site where the planet swallows its own crust, recycling water back into its depths. The restless Earth ensures that water remains part of its story, not just for a moment, but for billions of years. In the next chapter, we will look beyond the crust and into the skies, to see how atmosphere and water work together. Clouds, rains, and storms are not only products of the water cycle, but also partners in shaping the climate that makes Earth a water world. When we look up at the sky, we are not just seeing air. We are witnessing one of water's greatest partners, the atmosphere. Together, air and water weave a delicate dance that shapes weather, regulates climate, and sustains life. Without this partnership, Earth would not be the blue world we know. The atmosphere is a mixture of gases, mostly nitrogen and oxygen, with smaller amounts of carbon dioxide, argon, and others. But one of its most important components is invisible water vapor. Though it makes up only a small fraction of the air, water vapor drives many of the processes that shape our planet's surface. It carries heat, forms clouds, and falls as rain or snow. Consider evaporation. When the sun warms the oceans, water molecules gain enough energy to escape into the air. This invisible vapor rises, carrying heat with it. As the vapor cools higher in the atmosphere, it condenses into droplets, forming clouds. When the droplets grow heavy, they fall as rain or snow, returning water to the surface. This cycle repeats endlessly. Powered by sunlight and balanced by gravity, it is one of the simplest yet most powerful systems on Earth. The atmosphere does more than move water. It regulates how much of it exists in each form. Clouds, for instance, play a dual role. They reflect sunlight back into space, cooling the surface, while also trapping heat beneath them, warming the surface. This balance determines global temperatures, which in turn decide how much water is liquid, frozen, or vapor. Too much heat and oceans would evaporate. Too little and they would freeze. Thanks to the atmosphere, Earth has remained in the sweet spot for billions of years. Storms are another example of this dance. When warm, moist air rises, it cools and condenses, releasing heat. This heat fuels powerful winds and towering clouds. Thunderstorms, hurricanes, and monsoons are all expressions of water and air interacting. These storms may bring destruction, but they also distribute heat and moisture around the planet, preventing extremes. The atmosphere ensures that water does not remain static, but circulates, renewing soils, feeding rivers, and sustaining ecosystems. Water also shapes the chemistry of the atmosphere itself. As rain falls, it dissolves gases and minerals, carrying them to the surface. Over time, this process helped reduce the amount of carbon dioxide in the air, cooling the planet and making it more habitable. In return, the atmosphere shields water from being lost to space. Without the blanket of air, ultraviolet radiation from the sun would break water molecules apart, and solar winds would sweep them away. The atmosphere, fragile as it seems, is a guardian of Earth's water. Life, too, has joined this dance. Plants release water vapor through transpiration, adding moisture to the air. Forests act as natural humidifiers, pumping vast amounts of water into the atmosphere each day. Even animals contribute through breathing and sweating. The biosphere is not separate from the water cycle. It is a participant together. Life and atmosphere keep water moving, balanced, and abundant. It is worth noting how rare this system is. Mars once had rivers and lakes, but its thin atmosphere could not hold water vapor. Over time, most of its water escaped into space. Venus has a dense atmosphere, but its heat prevents liquid water from existing at all. Earth alone balances temperature, pressure, and chemistry in such a way that water can exist in all three forms: liquid, solid, and gas, interacting in a graceful cycle. As you drift towards sleep, imagine watching the Earth from above. See clouds drifting across oceans, their shadows darkening the waves below. Picture storms swirling, rains falling, rivers swelling. Imagine the invisible vapor rising from forests, fields, and seas, joining the endless flow of the atmosphere. Every breath of air, every drop of rain, every wisp of cloud is part of this eternal partnership. The dance of atmosphere and water is not only about balance, but also about resilience. For billions of years, this system has endured, adapting to changes in sun, land, and life. It has weathered ice ages and warm periods, volcanic eruptions, and asteroid impacts, yet it continues to cycle, to balance, to sustain. In the next chapter, we will see how this dance between air and water set the stage for something even greater: the bond between water and life. From the first microbes in ancient seas to the forests and animals of today, water is not simply a backdrop. It is the very essence of life itself. Water is not just a feature of Earth. It is the stage upon which life began and the medium in which it thrives. From the first flickers of biology billions of years ago to the forests, oceans, and human bodies of today, water has been the thread weaving life together. Without it, life as we know it could not exist. The bond between life and water is unbreakable, fundamental, and profound. To understand this bond, imagine the earliest oceans. Around 3.8 billion years ago, Earth's seas were very different from those of today. Hotter, more acidic, filled with dissolved minerals and gases. Yet within these waters, chemistry stirred. Simple molecules collided, combined, and broke apart. In time, complex organic compounds emerged: amino acids, lipids, and nucleotides, the building blocks of proteins, membranes, and DNA. These reactions required a solvent, a medium that could dissolve substances, bring them together, and allow them to interact. Water was that medium. Water's ability to dissolve so many substances makes it the perfect environment for chemistry. Inside a drop of water, countless molecules can move, meet, and react. This fluidity allowed early molecules to form membranes, enclosing themselves into tiny compartments, protocells. Within these structures, life's first steps were taken. Without water's unique chemistry, such processes might never have happened. As life evolved, water remained central. Single-celled organisms floated in seas, drawing nutrients from the water around them. Photosynthetic microbes released oxygen into the atmosphere, forever changing the chemistry of both water and air. In time, multicellular organisms appeared, still bound to the seas. Even when life eventually moved onto land, it carried water with it. Every cell in every plant and animal is a tiny bag of water, continuing the chemistry that began in ancient oceans. Consider your own body. About 60% of you is water. Blood is mostly water, carrying oxygen, nutrients, and waste. Cells are filled with water, where countless reactions occur every second. Water cushions joints, regulates temperature, and helps transmit signals in your nervous system. Life is not just surrounded by water, it is built from it. You are, in a very real sense, a walking ocean. Water also shapes ecosystems. In rivers and lakes, it connects communities of fish, insects, and plants. In oceans, it supports coral reefs, kelp forests, and migrating whales. On land, rainfall sustains forests and grasslands, while deserts form where water is scarce. The distribution of water determines where life can flourish and where it struggles. Civilizations, too, have always gathered near water, rivers, lakes, and coasts. Because it sustains agriculture, trade, and health, the unbreakable bond between water and life is also evident in evolution. Fish evolved in seas, amphibians bridge the gap between water and land, and mammals, including humans, still rely on water for survival. Some animals return to the oceans: whales, dolphins, seals, showing that even when life left the seas, the pull of water remained strong. But why is water so uniquely suited for life? Beyond being a solvent, it has properties that stabilize environments. Its high heat capacity smooths out temperature swings, making oceans a safe cradle for delicate organisms. Ice floats, protecting aquatic life during freezes. Water's surface tension allows insects to stride across ponds and helps plants draw water upward from their roots. These properties, unusual among liquids, make Earth habitable and life possible. When scientists search for life beyond Earth, they look first for water. Mars, Europa, Enceladus, and distant exoplanets all intrigue us because they show evidence of liquid water or ice. The reasoning is simple. Where there is water, there may be life. This does not mean life elsewhere must mirror life on Earth, but it suggests that water is a universal solvent, a common stage upon which life's play can unfold. As you drift into calm, imagine those first oceans under alien skies, silent but full of potential. Picture molecules swirling in water, colliding and joining, until one day the first cell emerged. From that humble beginning came every tree, every bird, every human being. Water was there at the start, and it remains with us now, in every breath and heartbeat. Think also of the continuity. The water in your body is ancient. The molecules in your cells may once have drifted in primeval seas, frozen in glaciers, fallen as rain on forests, or flowed in rivers long gone. Water connects you to the earliest life and to the future yet to come. It is the common thread of existence. The bond between life and water is not just scientific, it is deeply poetic. To drink, to swim, to listen to rain is to connect with something eternal. Water does not merely support life, it is life's companion, its partner, its essence. In the next chapter, we will see how water and life reshape the planet together. For as life released oxygen into the atmosphere, it altered the chemistry of oceans and skies, creating a new balance and setting the stage for even more complex forms of life. The bond between life and water grew stronger as living organisms began to reshape the very chemistry of Earth. One of the most dramatic changes in our planet's history was the Great Oxygenation Event, sometimes called the Great Oxidation. About 2.4 billion years ago, life in the oceans began releasing oxygen on a scale large enough to transform the atmosphere, the seas, and the destiny of all living things. Water played a central role in this transformation. The story begins with tiny organisms called cyanobacteria. These simple microbes lived in shallow oceans, drawing energy from sunlight. Through photosynthesis, they used water, carbon dioxide, and light to produce sugars for food. In the process, they released oxygen as a byproduct. At first, this oxygen did not accumulate in the atmosphere. Instead, it reacted with iron dissolved in seawater, creating rust-like minerals that sank to the ocean floor. Over millions of years, these reactions produced thick layers of banded iron formations, many of which we still find in rocks today. Eventually, the ocean's supply of dissolved iron ran low. Oxygen could no longer be absorbed so easily, and it began to build up in the water and then in the air. This shift was profound. For the first time, Earth had a significant atmosphere of oxygen. The sky and seas were no longer the same. At first, oxygen was toxic to many early organisms. Life had evolved in an oxygen-poor environment, and the new gas disrupted chemical systems. Many species died out, while others retreated to oxygen-free environments deep in mud or inside rocks. But oxygen also opened new possibilities. Organisms that adapted to use it gained access to far more efficient energy systems. This set the stage for the evolution of complex life, including plants and animals. The Great Oxygenation Event also changed the chemistry of water itself. Oxygen in the oceans allowed for new reactions, altering nutrient cycles and the availability of minerals. It influenced the acidity of seawater and helped create stable conditions for more diverse ecosystems. With oxygen came ozone in the upper atmosphere, forming a protective shield against harmful ultraviolet radiation. This shield allowed life to spread into new environments and eventually onto land. Geological evidence of this event is striking. Rocks older than 2.4 billion years contain minerals that could only form in oxygen-free conditions, while younger rocks show clear signs of oxidation. The transition marks one of the sharpest divides in Earth's history, sometimes called the oxygen revolution. It was as if the planet itself turned a page, moving from one chapter of existence to another. For water, the change was equally profound. Oceans became layered, with oxygen-rich surfaces and deeper oxygen-poor zones. Nutrient cycles shifted, supporting new types of microbes and paving the way for eukaryotes, the more complex cells that would eventually give rise to plants and animals. Without the oxygenation of water, the evolution of complex life might never have happened. As you rest, consider how extraordinary this is. Simple microbes floating in shallow seas released a gas that transformed the entire planet. They altered the chemistry of water, the composition of the air, and the future of evolution. In a sense, life reshaped its own environment, creating conditions for even more life to flourish. Water was both the medium and the messenger, carrying oxygen across oceans and skies. The Great Oxygenation Event also serves as a reminder of how fragile balance can be. For billions of years, Earth had little oxygen. Then, through slow accumulation, the balance tipped and everything changed. Even today, the levels of oxygen and carbon dioxide in our atmosphere are regulated by water, life, and geology together. The dance continues, as delicate and powerful as it was billions of years ago. Imagine those ancient seas bubbling with oxygen for the first time. Picture iron settling to the ocean floor, painting the sea with layers of red and gray. Imagine skies slowly shifting, clouds drifting above a world beginning to breathe. It was not a sudden event, but a gradual transformation, stretched across millions of years, yet monumental in its impact. In the next chapter, we will turn to another form of water, ice. For while liquid water filled seas and rivers, frozen water began to shape landscapes, climates, and even the rhythm of Earth's history. Glaciers, snow, and polar ice would become architects of continents and guardians of the planet's climate balance. When we think of water, we often picture oceans, rivers, or rain. But water has another form that is equally powerful: ice. Frozen water has shaped Earth's landscapes, carved its valleys, and regulated its climate. From the frozen poles to the highest mountains, ice, snow, and glaciers remind us that water is not only liquid but also solid, and that in this form it becomes one of the greatest sculptors of the planet. The unique property of water, that it expands when it freezes, gives ice its power. Because ice is less dense than liquid water, it floats. This simple fact makes Earth's climate stable. When lakes or oceans freeze, the ice forms on the surface, creating a protective layer that insulates the liquid below. Without this property, bodies of water would freeze from the bottom up, trapping and destroying life. Instead, ice preserves ecosystems through winter and cold ages, allowing life to endure. Glaciers, rivers of ice, are among the most dramatic expressions of frozen water. They form where snow accumulates year after year, compressing into dense ice that begins to flow under its own weight. Glaciers move slowly, but their power is immense. As they grind across land, they carve valleys, transport rocks, and reshape continents. The fjords of Norway, the Great Lakes of North America, and countless other landscapes are legacies of glacial action. Each tells a story of ice advancing and retreating, sculpting Earth's face. Ice also plays a critical role in regulating climate. Polar ice caps reflect sunlight back into space, helping keep the planet cool. This reflectivity, known as albedo, makes ice a natural thermostat. When ice spreads during ice ages, global temperatures drop further, reinforcing the cycle. When ice retreats, more sunlight is absorbed, warming the planet. In this way, frozen water influences not only local conditions, but also global climate patterns. Throughout Earth's history, ice has come and gone in great cycles. The planet has experienced several major ice ages, when glaciers stretched across continents. These ice ages shaped ecosystems, migration patterns, and even human history. During the last ice age, which ended about 12,000 years ago, massive ice sheets covered much of North America, Europe, and Asia. As they melted, they released vast amounts of water, raising sea levels and creating the coastlines we know today. Snow, though gentler than glaciers, is equally important. It blankets landscapes, storing water in frozen form through winter and releasing it slowly in spring melts. This cycle sustains rivers, feeds agriculture, and balances ecosystems. In mountainous regions, snow is a reservoir, silently gathering in winter and feeding valleys in summer. Without snowmelt, many regions of the world would lose their main source of fresh water. Ice also tells stories of the past. Layers of ice in Greenland and Antarctica preserve tiny bubbles of ancient air, trapped as snow fell and compacted over millennia. By drilling deep cores, scientists can read these layers like pages in a book, learning about Earth's climate going back hundreds of thousands of years. These ice records reveal past cycles of warming and cooling, levels of carbon dioxide, and even evidence of volcanic eruptions and cosmic events. Frozen water is not just a sculptor of land, it is an archive of time. As you imagine drifting into rest, picture vast glaciers sliding silently across landscapes, carving valleys with patience beyond imagination. Picture snow falling gently, blanketing the land, muffling sound, and storing life-giving water for future days. Picture polar caps gleaming in sunlight, guarding the planet's balance. Frozen water may seem still, but it is always in motion, shaping land, reflecting sunlight, recording history. The presence of ice also highlights Earth's uniqueness. On Mars, frozen water exists at the poles, but without a thick atmosphere or active cycle, it remains locked and barren. On Europa and Enceladus, moons of Jupiter and Saturn, ice hides oceans beneath. On Earth, by contrast, ice interacts dynamically with atmosphere, oceans, and life. It melts, flows, refreezes, and cycles endlessly. It is part of a living system, not a frozen wasteland. Water in solid form is as essential as water in liquid or vapor. It shapes, it regulates, it remembers. From the snowflake that melts on your hand to the glacier that carves a continent, frozen water is one of Earth's greatest forces. In the next chapter, we will step back and compare Earth's water to that of other worlds. For while our planet thrives with oceans, rivers, and ice, our neighbors tell different stories of lost waters, frozen deserts, and parched surfaces. By comparing them, we learn why Earth became the blue planet while others did not. From space, Earth shines blue. Oceans cover most of its surface, clouds swirl in its skies, and ice caps gleam at its poles. It is no wonder astronauts call it the blue planet. Yet when we look at our cosmic neighbors, we see starkly different stories. Venus, nearly the same size as Earth, is bone dry, wrapped in a choking atmosphere. Mars, smaller but once promising, is now a frozen desert. Even moons and asteroids hold water in strange forms, but none resemble Earth's dynamic oceans. Why did Earth become the watery world, while others did not? The answer lies in location, chemistry, and balance. The first difference is Earth's position in the solar system. Earth orbits in what scientists call the habitable zone, the region where temperatures allow liquid water to exist on the surface. Too close to the sun and water boils away, as it did on Venus. Too far, and it freezes solid as on Mars. Earth's orbit places it in the sweet spot. But distance alone is not enough. Venus and Mars once may have had water, yet they lost it. Earth held on. Atmosphere explains much of the difference. Venus has an atmosphere 100 times thicker than Earth's, dominated by carbon dioxide. This traps heat in a runaway greenhouse effect, raising surface temperatures high enough to melt lead. Any oceans Venus once had boiled away, their molecules split by sunlight. Hydrogen, the lightest element, escaped into space, leaving the planet dry. Mars, by contrast, has an atmosphere far too thin to hold heat or pressure. Water there either froze or evaporated into space. Earth's atmosphere, rich in nitrogen, oxygen, and water vapor, maintained a balance, shielding oceans while supporting life. Earth's magnetic field also played a role, generated by motion in the liquid iron core. This magnetic shield protects the planet from solar winds, streams of charged particles from the sun. Without it, those winds strip atmospheres away, as happened on Mars. By preserving its atmosphere, Earth preserved its water. Our planet's invisible shield is one of the unsung guardians of the oceans. Chemistry adds another layer. Earth's rocks and minerals interact with water in ways that regulate its presence. Subduction zones recycle water into the mantle, while volcanoes release it again. This balance prevents either total loss or overwhelming floods. Venus lacks active plate tectonics, so its carbon dioxide built up unchecked. Mars, with less tectonic activity, could not sustain long-term recycling. Earth's restless geology may be the very reason its water endured. The presence of life itself further distinguishes Earth's water. From cyanobacteria releasing oxygen to forests pumping vapor into the sky, biology and water form a feedback loop. Life helps shape the water cycle, just as water shapes life. No other planet we know has this partnership. Oceans on Earth are not only physical features. They are living systems, enriched by organisms, balanced by ecosystems, and influenced by biology. This connection adds resilience, keeping water flowing through countless cycles. Looking beyond the inner planets, we see other forms of water. The icy moons Europa and Enceladus hide vast oceans beneath frozen shells. Their water is real, perhaps even liquid, but it is locked beneath kilometers of ice, isolated from the surface. Titan, Saturn's largest moon, has lakes not of water, but of methane and ethane. Comets wander with tails of vaporized ice, but they are too small to sustain seas. In all these cases, water exists, but never as openly and dynamically as on Earth. Another striking difference lies in scale. Earth's oceans contain around 1.4 billion cubic kilometers of water. That may sound vast, yet compared to the size of the planet, it is a thin film, less than 0.1% of Earth's mass. Still, that film is enough to cover most of the surface, drive the climate, and sustain life. On other worlds, water is either trapped deep inside, frozen at the surface, or lost entirely. Earth alone displays it in abundance and motion. The isotopic fingerprint of Earth's water also sets it apart. By studying the ratio of hydrogen isotopes, scientists have compared ocean water to meteorites and comets. While there are similarities, Earth's oceans show a distinctive blend, suggesting a unique history of delivery and recycling. This fingerprint is part of what makes Earth's water unlike any other, the product of a specific mix of cosmic gifts and planetary processes. As you rest, picture Earth seen from space. Blue oceans gleam, white clouds drift, green continents break the surface. Now picture Venus, cloaked in yellow haze, its surface scorched and dry. Picture Mars, rust red with traces of ancient rivers now silent. Picture icy moons, their surfaces cracked, hiding oceans no light has ever touched. In this gallery of worlds, Earth is the exception, the one where water flows freely and visibly. The uniqueness of Earth's water is more than a scientific puzzle, it is a wonder. Oceans not only exist, but they shimmer, roar, and breathe with life. Rivers carve valleys, rains feed forests, glaciers sculpt mountains. Every form of water is present, from vapor and clouds to ice at the poles to the vast liquid expanses in between. This diversity is unmatched elsewhere in the solar system. Why does this matter? Because it reminds us how fragile our balance is. Earth's oceans exist not because water is common, but because so many conditions align: distance, atmosphere, magnetism, tectonics, and life. Remove any one of these, and Earth might look like Venus or Mars. Our seas are not inevitable. They are a rare and precious outcome. In the next chapter, we will explore more closely those neighboring planets, Venus and Mars. By studying their lost waters, we gain perspective on what makes Earth's story unique and what it takes for a planet to keep hold of its most vital element. When we look at Earth's neighbors, Mars and Venus, we see two planets that might have been blue worlds like ours, but are not. Their histories are stories of water lost, climates gone astray, and fragile balances broken. By studying them, we learn not only about what could have been, but also about how rare and precious Earth's oceans truly are. Let's begin with Mars. Today it is a cold desert world, its skies thin and dusty, its surface etched with valleys, craters, and plains. But billions of years ago, Mars was different. Orbital images show dry riverbeds winding across the land, deltas frozen in stone, and minerals that form only in the presence of water. These clues reveal that Mars once had lakes, perhaps even shallow seas. Rains may have fallen, rivers may have flowed, and for a time, Mars may have been wet. So where did its water go? The answer lies partly in size. Mars is smaller than Earth, only about half the diameter and 1/10 the mass. With less gravity, it struggled to hold onto its atmosphere. Over time, solar winds stripped the air away. Without thick air to trap heat, the surface grew colder, and liquid water froze or evaporated. Hydrogen from broken water molecules escaped into space, leaving Mars dry. What remains now is locked as ice in polar caps or hidden underground, silent reminders of oceans long gone. Venus tells a very different story. Almost the same size as Earth, Venus likely began with similar amounts of water, but its fate diverged dramatically. Being closer to the sun, Venus received more heat. Water evaporated into the atmosphere, where sunlight split molecules apart. Hydrogen escaped into space, while oxygen reacted with surface rocks. Meanwhile, volcanic eruptions pumped vast amounts of carbon dioxide into the air. With no plate tectonics to recycle it, the gas built up, creating a runaway greenhouse effect. Temperatures soared high enough to melt lead, and any oceans Venus once had were lost forever. Today, Venus is a world of crushing pressure, suffocating clouds of sulfuric acid, and a surface baked beyond recognition. Radar images show ancient plains and mountains, but no seas, no rivers, no lakes. If Earth is the story of water preserved, Venus is the story of water boiled away. Together, Mars and Venus show us two paths that Earth could have taken. Mars teaches us about loss through weakness, a world too small to hold on to its atmosphere, its water stolen by space. Venus warns of loss through excess, a world overwhelmed by greenhouse gases, its water boiled into oblivion. Earth alone navigated the narrow path between these extremes. These comparisons also sharpen our understanding of habitability. Water is not enough. A planet must hold the right balance of size, atmosphere, magnetic shield, and geology. Mars had water, but not the protection to keep it. Venus had water, but not the balance to regulate it. Earth had both. That difference is why we gaze at seas while Mars and Venus remain barren. Scientists continue to search for traces of water on both worlds. On Mars, orbiters and rovers have found clays, salts, and ice, evidence of past rivers and possible underground reservoirs. Some speculate that briny liquid water may still flow beneath the surface, hidden from view. If so, it could harbor microbial life, clinging to the last refuge of water. On Venus, spacecraft have searched its dense clouds for chemical signatures that might hint at unexpected processes. While unlikely to host oceans, Venus may still hold secrets about water's role in its distant past. The lessons of Mars and Venus reach beyond curiosity. They serve as warnings. On Mars, we see the danger of losing an atmosphere. On Venus, we see the consequences of unchecked greenhouse gases. Earth exists between these two fates, balanced yet vulnerable. Our oceans depend on conditions that can shift, reminding us how fragile habitability truly is. As you rest, picture Mars as it might have been, a world with blue skies, rivers winding through valleys, and lakes shimmering in craters. Picture Venus as it might have been, clouds reflecting sunlight, oceans sparkling beneath. Then picture how both changed: Mars frozen, Venus scorched, their waters gone. In their silence, they remind us how rare Earth's story is. Water connects all three planets, even in absence. Earth's oceans, Mars's ancient rivers, Venus's vanished seas. They are chapters in a larger story of how planets live and die. To understand water on Earth, we must look at where it was lost elsewhere. The comparison makes clear that our oceans are not inevitable, but extraordinary. In the next chapter, we will widen our gaze even further. Beyond Mars and Venus, beyond the solar system, astronomers search for planets around distant stars. They ask the same question we ask here: where did water come from? And could it make life possible beyond Earth? The search for exoplanets is, in many ways, a search for water across the universe. For most of human history, Earth seemed like the only world with seas, rivers, and clouds. Stars shone as distant lights, but no one knew whether planets circled them, let alone whether those planets held water. Today, thanks to modern telescopes and missions, we know thousands of exoplanets, planets orbiting other stars. And in many ways, the search for these distant worlds is a search for water. If water exists beyond Earth, then perhaps life does too. The discovery of exoplanets began in the 1990s and has since exploded into one of the most exciting fields of astronomy. Planets are detected by subtle shifts in starlight, as when a planet passes in front of its star and slightly dims the light we see. These tiny signals reveal the size, orbit, and sometimes even the atmosphere of distant worlds. Among the many discovered, some lie in the habitable zone, the region where temperatures could allow liquid water to exist. But finding a planet in the habitable zone is only the beginning. Water depends on more than distance. A planet must have the right atmosphere, the right pressure, and the right chemistry. Without these, water may boil away or freeze, as we see with Venus and Mars. Astronomers use models to estimate whether exoplanets could keep oceans, but direct evidence remains rare. Still, every new discovery brings us closer to answering the question: is Earth unique? Some exoplanets are strikingly Earth-like. Kepler 52b, often called Earth's cousin, orbits a star similar to the Sun in a zone where water might flow. Others, like TRAPPIST-1's 7 planets, offer tantalizing possibilities. Several of those worlds are in the habitable zone, and because they orbit a nearby star, astronomers can study their atmospheres with powerful telescopes. Imagine not just one, but a system of planets where water might exist in rivers and seas. Water beyond Earth might also take forms we cannot easily imagine. Some exoplanets may be water worlds, covered entirely by oceans without landmasses. Others might have icy shells like Europa, with oceans hidden beneath. Still others might host superheated atmospheres where water exists as vapor. The diversity of worlds challenges our imagination, reminding us that water is versatile, capable of shaping planets in many ways. Technology now allows us to study exoplanet atmospheres by analyzing starlight passing through them. Molecules absorb specific wavelengths of light, leaving fingerprints astronomers can detect. Already, water vapor has been found in the atmospheres of some giant exoplanets. These worlds are too hot or too large for life as we know it, but their discovery proves that water is not confined to Earth. It exists, drifting as vapor even around distant suns. The presence of water raises the next question: what about life? Life on Earth depends on water, and so astronomers use it as a guide. If water is found on an exoplanet, the odds of life increase. Yet life might also surprise us, perhaps adapting to solvents other than water. For now, however, water remains our best clue, the universal stage for biology. As you rest, picture the vastness of the galaxy. Around every star, planet circle. Some are giant and barren, some scorched, some frozen. Yet among them, perhaps, are worlds with seas reflecting alien skies, clouds drifting across strange horizons, rain falling on unfamiliar ground. Imagine looking up from one of those shores, seeing 2 suns or red skies, yet hearing the same rhythm of waves. Water may be the thread that binds distant worlds to our own. The search for water on exoplanets is not only scientific, it is also deeply human. It speaks to our longing to know whether we are alone. If another world holds oceans, then perhaps life also stirs there, watching alien skies, wondering about us. Water becomes a bridge linking Earth to distant possibilities. This search also teaches us humility. Earth's oceans exist not by chance but by a balance of many factors. When we look for water elsewhere, we realize how fragile and rare such balance is. Even if water proves common, the harmony that sustains oceans and life may be rare indeed. The very act of searching reminds us to cherish the seas we have. The story of exoplanets is still young. Each year brings new discoveries, sharper telescopes, and deeper questions. Soon we may detect not just water vapor but oceans themselves, perhaps even biosignatures, clues of life. Until then, the dream continues, to find another blue planet circling a distant star, glowing with seas like ours. In the next chapter, we will return from distant space to Earth's future. Our oceans, though vast, are not guaranteed forever. Climate change, melting ice, and shifting balances threaten them. By understanding their past and comparing them with other worlds, we gain insight into how to protect them for the ages to come. The oceans of Earth have endured for billions of years. They have weathered asteroid impacts, ice ages, and shifts in continents. They have given rise to life, moderated climate, and carved landscapes. Yet their future is not set in stone. Like everything on Earth, the oceans are dynamic, shaped by forces both natural and human. To understand where our seas are heading, we must consider both the rhythms of the planet and the choices of humanity. On geologic timescales, the oceans will continue to evolve with plate tectonics. Continents drift, colliding to form supercontinents and splitting apart again. Each cycle reshapes the ocean basins, altering currents and coastlines. In another 200 million years, Earth's landmasses may once again gather into a single supercontinent, surrounded by a vast ocean. This process has happened before and will happen again, as the restless crust reshuffles the seas. But on human timescales, decades to centuries, the oceans face challenges more immediate. Climate change, driven by rising greenhouse gases, is altering the balance of air and water. As temperatures rise, polar ice melts, adding fresh water to the seas. Glaciers retreat and ice sheets shrink, raising global sea levels. Already, coastlines are shifting, wetlands are drowning, and storms are intensifying. Entire communities must adapt to a new rhythm of rising tides. Warmer oceans also expand, increasing sea level further. They absorb much of the excess heat trapped by greenhouse gases, buffering the atmosphere but paying a price themselves. Coral reefs bleach, ecosystems shift, and marine species migrate toward cooler waters. The oceans remain vast, but their chemistry and biology are changing. Another threat is acidification. As carbon dioxide dissolves in seawater, it forms carbonic acid, lowering the pH. This makes it harder for organisms like corals, clams, and plankton to build shells and skeletons. Because these creatures form the base of ocean ecosystems, their struggle ripples upward through the food web. Acidification is a reminder that the chemistry of water, delicate though it seems, underpins life on Earth. Yet the future of the oceans is not only about danger, it is also about possibility. Humans have the power to alter outcomes. By reducing emissions, protecting ecosystems, and managing resources, we can safeguard the seas. Marine reserves give species room to recover. Clean energy reduces the burden on oceans. Better stewardship can sustain fisheries, coral reefs, and coastlines. The future of the oceans depends as much on human choice as on natural cycles. Looking further ahead, the fate of Earth's oceans will also be tied to the life of the sun. In about 1 billion years, as the sun grows brighter, Earth may warm beyond the ability of oceans to endure. Water will gradually evaporate, molecules will break apart, and hydrogen will escape into space, as it did on Venus. Long before the sun becomes a red giant, Earth may lose its seas. This distant fate is inevitable, part of the cosmic cycle, but it lies far beyond human timescales. As you rest, picture the oceans as they are today. Waves rising and falling, tides moving in rhythm with the moon, storms swirling, life thriving. Then imagine coastlines centuries from now, reshaped by rising seas. Imagine future generations looking out at waters we know, wondering what choices their ancestors made. The future of the oceans is not only about physics, it is about responsibility. The oceans connect everything. They regulate climate, feed billions, and shape cultures. Their future is our future. If they thrive, humanity thrives. If they falter, we falter. By caring for them, we care for ourselves and for all life that depends on water. In the final chapter, we will bring the story full circle. From cosmic origins to planetary cycles, from ancient rocks to distant exoplanets, from life's first stirrings to its uncertain future, the journey of water is the journey of Earth itself. The conclusion ties together what we have learned. reminding us why the question of water's origin is also the question of our own. Water is more than a substance. It is a story, ancient, unbroken, and eternal. To follow its path is to trace the history of Earth itself, from the chaos of a young solar system to the lives of billions today. As we conclude this journey, we see how water has always been more than simple molecules. It is the element that connects stars and planets, oceans and skies, rocks and life. It is the thread of continuity across deep time. We began with cosmic origins. Hydrogen, the simplest element, was born in the Big Bang. Oxygen formed later in the hearts of stars, forged in their fiery cores and scattered in supernova. When hydrogen and oxygen met in the cold depths of space, they formed water, tiny crystals of ice, carried on comets hidden in asteroids, drifting between stars. From this cosmic dust, solar systems emerged, and with them, the possibility of worlds like ours. On Earth, water arrived in many ways. Some was trapped in minerals as the planet formed. Some was delivered by icy bodies colliding with the surface. Some emerged from volcanic outgassing, rising as steam and falling back as rain. Over time, these sources filled basins, carved oceans, and wrapped the planet in seas. The result was a world transformed, a blue planet unlike any other in our neighborhood. But water did not stop at forming oceans. It shaped land, eroded mountains, and carved valleys. It cycled endlessly through air, rain, rivers, and seas. It moderated temperatures, stabilized climates, and gave rise to weather. With plate tectonics, it moved between surface and interior, recycled and renewed. The presence of water made Earth dynamic and alive, not static and barren. Most profoundly, water gave rise to life. In ancient oceans, simple molecules gathered and reacted, forming the first cells. In water, life learned to harness energy, replicate, and evolve. Even as organisms moved onto land, they carried water within, each cell a tiny ocean sustaining ancient chemistry. Life and water became inseparable. Without water, life as we know it could not exist. The story of water is also the story of transformation. The great oxygenation event, driven by microbes in the seas, changed oceans and skies forever. Ice ages carved continents, raising and lowering sea levels. Storms and rivers shaped civilizations, bringing both abundance and destruction. Oceans became the cradle of ecosystems, the highways of exploration, and the boundaries of empires. Humanity has always lived by the rhythm of water. Beyond Earth, water tells other stories. Mars, once wet, is now a frozen desert. Venus, once promising, lost its seas to runaway heat. Icy moons hide oceans beneath frozen crusts, whispering possibilities of life. Exoplanets orbit distant stars, some perhaps blue like Earth, some wholly alien. Water may be common in the universe. Yet Earth's balance remains rare, the perfect combination that sustains oceans in plain view. As we look to the future, water again becomes central. Climate change threatens seas with rising levels and shifting chemistry. Glaciers retreat, corals bleach, and ecosystems strain. The oceans, vast though they are, remind us of fragility. They can endure for billions of years, but they can also be reshaped in mere centuries. The choices humanity makes now will echo through the water cycle for generations to come. And yet, water also gives hope. It is resilient, cycling endlessly through forms, adapting to change. It has survived impacts, volcanoes, and ice ages. It will outlast us, continuing its story long after humanity is gone. Even when the sun grows too bright and oceans evaporate, water will remain in some form. Vapor in the air, traces in rocks, fragments in space. Its story is larger than ours. As you reflect, imagine the full arc of water's journey. See it born in stars, drifting through space, falling onto a young Earth. See it gathering into seas stirred by storms, glowing under alien skies. See life emerging, spreading, evolving, always carried by water. See civilizations rising on riverbanks, sailing across oceans, harnessing water for food, power, and survival. And see the future, where water remains the most precious thread of continuity, binding us to the past and to possibilities beyond Earth. Water is eternal, yet intimate. It is in the vast Pacific Ocean and in the glass you drink. It falls as rain, freezes as snow, and flows as blood. It connects stars to cells, geology to biology, past to present. It is not only the answer to where we came from, but also a guide to where we might go. So when we ask, where did Earth's water come from? We are asking more than a scientific question. We are asking about origins, about meaning, about connection. The answer is not a single source but a tapestry. Cosmic ice, volcanic breath, ancient rains. Together they formed oceans, which in turn formed us. The story of water is the story of Earth. It is also, in a sense, the story of us. To understand it is to understand our place in the universe. To protect it is to honor the thread that makes life possible. As the journey closes, imagine drifting on calm seas under a starlit sky. Above you shine the same stars that forged oxygen, that gave birth to water. Around you waves carry whispers of ancient rains, ancient rocks, ancient lives. Within you water flows, connecting you to oceans billions of years old. The story is not ending, it continues eternal as water itself.